Let's jump into it. Welcome to my session, behind schedule, pod resource configuration from beginning to... I'm sure we've all had that moment where we thought that something was going to start running and it did not, and it didn't seem like it did so for a reason that made any sense at all. Oh, yes. So let's do a little bit of introduction. I'll tell you a little bit about myself, although not too much, so we don't take up too much time. I like to take the temperature of the room a little bit as I get started too, and then kind of what are we here for today. So before we get started, and for real, it's really dry out there. If you just flew in last night and you woke up this morning and your throat felt like the desert outside, Salt Lake City and Utah are one of the driest areas in the US. Please, for your own health and safety, drink water constantly the whole time you're here. There's water bottle swag at plenty of vendors, I'm sure. Go buy one from the CNCF store if you need one. Definitely, it is worth your time. It's worth your time and attention to make sure that you're getting enough water here. So who am I? My name is Joe Thompson. I've been working in IT overall for almost 30 years, depending on how you count. I usually count from December of 1995. That was my first full-time paying IT job. Along the way, to get to today, I've worked for Red Hat, CoreOS, Mesosphere, HashiCorp, some of the names people in the room might know. Currently, I am a consulting engineer for a company called Clarity Business Solutions. They're based fairly near DC, and the part of the company that I work in is their MongoDB partnership. We provide escalation support for MongoDB customers, among other things. My basic pronouns right there. The pop culture reference center of gravity is fairly important. If you're talking to me, you will eventually get a movie reference to like a John Hughes movie or Office Space or something like that. And there's some contact info there. Now, as far as people in the room, I see we still have some people coming in, but it looks like we're pretty full up now. Who here, this is your first KubeCon? Okay, yeah, usually a lot of hands go up for that. Who here has been working with Kubernetes for less than a year? Okay, keep your hands up. Put your hands down if you've been working more than 6 months. Who here still is? Okay, so we have a few that are really, really new to this. So great, because this is very much a basics talk, but it does get into kind of like as you're learning the basics, you hit that odd moment and you go, wait, that's not right. And it is right. It's very simple behavior and it has its own internal logic, but you kind of have to understand what that logic is. So the very basics of resources, if you've been working with Kubernetes for any length of time at all, you know that requests are a floor for resource allocation. That is the minimum amount of whatever resource it is that those containers in that pod need before that pod will get scheduled on a node. If there isn't enough on that node, it won't get scheduled there. The limits are the opposite, they're the ceiling. If a container exceeds a limit, then it gets terminated. There's actually a little asterisk on that, which we'll kind of go into later. Requested resources that are unused or wasted resources. And I mentioned there's going to be an asterisk on termination. There are resources that are compressible and there are resources that are incompressible. So if you exceed the limit on an incompressible resource like memory, you just get terminated. If you try to exceed the limit on a compressible resource like CPU, you don't get terminated, you get throttled. Now, there is this thing called quality of service, and this is where, if you haven't been working with Kubernetes for very long, you may not have hit this yet. Quality of service is a classification of your pods that Kubernetes assigns. You don't set it. Kubernetes assigns it based on the requests and limits that you set. Now, in normal operation, just your pod running, doing its thing, what quality of service it has doesn't matter. It doesn't affect the running of the pod. It only comes into play when things start to get congested. And so those three classes of quality of service can be best effort, burstable, or guaranteed. Now, notice I put asterisks on no effect and also on guaranteed. There are footnotes there. When I say it has no effect on the operation of the pod, there actually are things that you cannot do unless you have the guaranteed quality of service class. Things that you are not allowed to access, like reserved CPUs. Guaranteed is not actually guaranteed in much the same way that a Kubernetes secret is not really a secret at all. Guaranteed just means that you won't get evicted for exceeding your limits. There are other conditions under which a guaranteed pod can actually be terminated and moved out of the way. Now, alongside of quality of service, there is the concept of priority. Priority is user controllable. Pods get a priority of 0 by default. And you normally don't refer to them by number, you refer to them by name. So you'll have a priority class that has a name that then maps to a numeric priority. And so you can map a very high priority, you can map a very low priority. By default, your cluster is going to have 2 very high priorities called system node critical and system cluster critical. And like quality of service, priority doesn't really affect your pod just running and doing its thing. So that's all fairly easy. There's some caveats and footnotes there, but it's going to get more complicated. Then it's going to get weird. Okay, so what happens when we start to put our clusters under resource pressure? We got too much freight on our railroad. Okay, so there is eviction and there is preemption. And they are different mechanisms that are kind of in the same category. They're both trying to make sure that the things that need to run can run, but they're coming at it from different directions. So eviction is triggered by the kubelet when the node comes under pressure. Now see, there's another asterisk there. There's going to be a footnote. Preemption is triggered by the scheduler when a high priority, I see I have a typo there. When a high priority pod can't be scheduled normally. There are not enough resources on any node in the cluster to just assign to that pod and schedule it. Then preemption kicks in. So the asterisk on under pressure, there is actually an eviction API request. You can just say, I want you to evict that pod. Whether or not you're under pressure, I just want you to evict it now. Now, where this starts to get complicated is scheduling is not a promise. So something gets preempted and kicked out of a node, and it goes back into the scheduler queue. But that doesn't mean it will actually get rescheduled. Something gets evicted and goes into the scheduler queue, there's no guarantee it will be rescheduled. All we're promised is that we'll end up back in the queue. It can stay in that queue arbitrarily long, especially if your cluster is under really heavy resource pressure. One way of buying your way out of that situation is by auto-scaling. Just put some more resources in the cluster so that things can happen normally, so that preemption and eviction are not in play anymore. Okay, so if you can't afford to buy your way out of it, what you may try to do is go and adjust your resource requests. But you can get into the situation where you say, oh, okay, I'm going to adjust my request down so that more things can run, and I'm not wasting as much resources. But then things start to get evicted more often because pods that exceed their requests are the first out the door. So if you adjust your request down too far, like people think of it as a floor and a ceiling, right? You want your request to be lower than what you normally consume, although not too much lower, and you want your limits to be the top of what you would normally consume. But really what you should do is you should set your request slightly higher than normal, and that way you won't trigger that first in line behavior of, oh, you're just slightly over your resource request. Over is over. Get out. So setting your request to the absolute floor can backfire on you. Preemption has a Don Draper moment. Anybody see that meme where it's Don Draper and the other guy in the elevator, and the guy says, I feel bad for you, and Don Draper says, I don't think about you at all. Well, eviction uses priority as part of its logic for which pods it's going to terminate and evict. Preemption does not care at all about quality of service. So you can end up with a situation where a high priority, best effort pod survives low quality of service, but a low priority guaranteed one gets booted out. It's not very guaranteed at that point. Preemption math, this one, I really had to look at this the first time I ran across it. I went, can that really be right? Before it tries to evict any pods on a candidate node, the scheduler will say, I have a pod of priority X. If I evict all of the nodes lower than priority X, or all of the pods lower than priority X on that node, will I be able to schedule this pod there? Now that makes a difference because there are cases where if you just evicted some of those pods, you would be able to schedule it, but evicting all of them makes that pod unschedulable because there are, for example, affinity rules or anti-affinity rules. And if you evict a pod that is the target of an affinity rule on the pod you're trying to schedule, now you can't schedule anymore. But it doesn't try to pick and choose. What it's doing, it's kind of considering a worst case scenario. It's trying to avoid a situation where it evicts and evicts and evicts and evicts, and then it ends up it can't schedule at all. So it evicted a bunch of pods for nothing. So it just considers that worst case scenario right up front. If the worst case scenario happens and I still can't schedule this thing, I'm not even going to try. Now, eviction has a Don Draper moment. Preemption will try to respect your pod disruption budgets. Pod disruption budget, for those who may not have run across that yet, that's where you say, I want to make sure that a certain number of this particular set of pod replicas is always running, or I want to set a maximum number that will be unavailable. There's a lot of detail there that's kind of beyond the scope of this, but that's basically what it is. It's a mechanism of protecting your application from too many of its replicas going offline all at once. Preemption doesn't care. Well, no, preemption does care. It will try to respect your pod disruption budgets, but it will still go ahead and knock things out if it can't. Node pressure eviction doesn't care at all. It won't even care about your termination grace period seconds. If it decides that this pod needs to go, it's gone. That API-initiated eviction that I mentioned before, that does respect pod disruption budgets. So there's, you'll see advice some places where they'll say you should be monitoring your nodes, and rather than let your nodes go into eviction, you should start proactively using the API eviction endpoint to evict pods proactively, because then your pod disruption budgets will be respected and you'll have less disruption overall. Now, how are we going to manage this whole mess? Okay, so the first rule is always keep it simple. Make sure that you can reason about the pods in your cluster. Make sure you know how are they going to get scheduled? Where are they going to get scheduled? What kind of node are they going to get scheduled on? Don't get too fancy with things. Don't go wild creating whole, intricate structures of priority classes or these huge complex affinity rules. Or, I've seen people create, like people who are using the Carpenter scheduler, they create just tons and tons and tons of different very, very specific node pools. And then it ends up biting them in later on when their rules are so specific that things can't get scheduled. Sometimes you may need to just consider whether you need separate node groups. Maybe you even need separate clusters for some purposes, just to make sure that the scheduling can stay simple, so that it can stay understandable. Use your pod disruption budgets. Don't count on them, though. Because, the other footnote to PDBs is they only protect you from voluntary disruption. If a node just hard goes down, PDB doesn't matter. There's nothing Kubernetes can do about a physical node failure. So, if you're counting on PDBs to be the end-all, be-all, they're not. This one, I almost didn't want to put this in here. You have to be really, really careful when you tune your eviction thresholds. And the reason is because if you tune them wrong, you're going to do one of two things. You're either going to have nodes that have a lot of wasted resources that can never get used, or you're going to have nodes that end up in such tight resource constraints that they're in danger of deadlocking. And remember that there are things on your nodes running other than Kubernetes pods, not only the Kubernetes components, but basic system components. And if your nodes end up in really bad resource constraint situations, some of those critical components that you consider critical outside of Kubernetes may end up getting killed. They're set relatively conservatively by default. So it is a tunable thing. Be very careful how you tune it. If you tune it, I would say lean more in the direction of tuning it conservatively rather than dangerously, because you can usually recover from spending too much money. It can be hard to recover from an application outage. Okay, so you've got all these great, clever ideas for what you're going to do about all this stuff. You got to test them. You got to test them in your test environment. And how many people in here have used a test environment where they work? You have one, okay? How many people in here, you either don't have one or you have never been able to use it? And I see a couple of hands. You've got one too. It's called production. There's you'll see some memes every now and then. People will go, yeah, go ahead and test in production, because effectively you are anyway. You can put things through as many different lower test environments as you want, but production is the acid test, as they say. So if all else fails, throw money at the problem. We all have infinite budgets, right? It's always easy to go back and say, I need another $100,000 for our AWS bill. Okay, because remember, in normal operation, none, asterisk, a few things do matter, and everything has enough resources to schedule. You want, ideally, to be in a situation where there is no eviction, there is no preemption, because everything is fully, adequately provisioned. All of your workloads are running. None of them are restarting. None of them are getting evicted or killed or, suffering from unmet affinity constraints or anything like that. That is the state you want to be in. Sometimes you just have to spend the money to get there. Now, I think I mentioned the Carpenter Autoscaler before. It will actually do a fairly good job of this. For those who've used the Cluster Autoscaler, it's not a 100% like you should stop using that and start using this. There are situations where the Cluster Autoscaler is more appropriate for whatever workload you're running, particularly because Carpenter doesn't support a lot of environments yet. But between the Cluster Autoscaler and Carpenter, you can usually make sure you have enough resources. Now, there are other autoscalers out there. Anybody here worked with, I'm not entirely sure the proper pronunciation of this. Kita? A few people here and there. Yeah, so you can autoscale your workloads with Kita. There's also the vertical pod autoscaler, which will go in and say, well, this pod has this huge amount of requests. It's not actually using them. It'll go in, it'll rescale that pod, and then that pod will restart using less requests. Later on, if it starts to grow beyond a certain threshold, VPA will say, well, we need to give it a little more headroom. It'll rescale it again. Tricky thing with VPA is the way it's written now, and I'll talk a little bit more about how that might change in the future in a minute. The way it's written now, you incur disruption when you use it. Because every time you use it, every time it scales a pod, it does so by that pod restarting. Remember that thing about infinite money? I don't remember where I heard this first, but somebody had this great quote that I saw in a presentation. They put it on a slide. It was, remember, auto-scaling is connected directly to your credit card. Okay, so there are a few things. I said it gets complicated, then it gets weird, right? It's going to get more complicated and weirder in the future, but in some ways, it's doing so in a good way. So let's talk a little bit about what's coming. Anybody here played with in-place pod resizing yet? A couple of people? So what I just said about the vertical pod autoscaler, that it causes your pod to restart, you're incurring disruption. You can protect yourself against incurring too much at once with pod disruption budgets. In-place pod resizing is an alpha feature in Kubernetes. It landed in, I think, 127. So it's been around for a couple of generations now. And it will actually allow you to resize a pod in place without a restart, so that you can squeeze it down. You can kind of squeeze the air out of it and make it so that other things can run on that node. And I saw an issue in the vertical pod autoscaler GitHub project about it. As soon as it goes GA, if it goes GA, they really, really, really want to use it. Now, don't expect that to land as GA or even beta. It's still not even beta yet. Don't expect it to land as beta in like 1.2 or anything. It's still got a ways to go. It's still not fully baked, but it's there. You can turn on the feature gate, you can play with it, you can see, how your workloads tolerate it. There are some workloads that won't tolerate that kind of thing. Particularly things like resizing the memory on a database, that can be very dangerous. Resizing CPU, less dangerous, because again, CPU just gets throttled. You just have to make sure that you're providing adequate CPU for things to happen fast enough they need to happen. Dynamic resource allocation, it's not strictly part of what I'm talking about today, but it does kind of exist in that same universe. If you look around the last couple of releases of Kubernetes, there's been a lot of implementation. I think the big implementation that I saw was in 127, and there's been some significant refinements since then. It's kind of an abstraction of storage to other resources, so other resources like GPUs. So it doesn't really come into play necessarily with what I'm talking about with priority and eviction and that kind of thing, but it does come into play when you start talking about what is going to schedule where and what might prevent things from scheduling different places. Now this last one, this is really cool. I'm really excited about this. I've kind of been sniffing around this one for a while. There is a thing called CRYU, Checkpoint and Restore in User Space, which allows you to take a snapshot of a container and then take it somewhere else, and at least in theory, restore from that snapshot. Now, to do that in Kubernetes is very complicated because there's a lot more than just the container itself going on. There's networking outside the container, there's possibly open connections, there's all kinds of other things attached to that running container. During Cloud Native Rejects, Sunday, I think it was Sunday, I saw somebody do a demo of live pod migration with active running connections from one cluster to another. Just took the whole pod, boop, over there, on a whole different cloud, and everything kept running. What he actually did when he did his demo, he set up a transaction in Postgres, then he migrated the pod, then he completed his transaction, and it completed successfully. Now again, this is something that is not necessarily 100% ready to rock and roll yet, but it's getting there, it's coming. So I'm really excited about that. Oh, let's see, model railroading. Let's do a real quick demo here. This, by the way, is being run by Demo Magic for anybody who needs a nice little demo script thing. It's great because it's not replaying a recording, it's actually doing it live. So everything I'm doing right now is being done on my live cluster. Okay, actually, let me do one thing before that. This is how you know it's not faked. Okay, now let's repeat. Okay, so empty cluster, other than the default stuff that's running. This is a one node cluster in DigitalOcean. And it's a very small node. You can see down here at the bottom, I'm using 702 millis, whatever you want to call it, of CPU, and that's about a third. So I've got something less than 2 full CPUs available to allocate here. So this is a regular old, just nothing, it's just running the pause container. It's requesting 1 CPU to do nothing with. And this is a high priority. In fact, you can see right up here, system cluster critical. I said there were two high critical priorities that are built into the cluster. System cluster critical and system node critical. Pop quiz, which one of those is higher? Hands up everybody who thinks system cluster critical is higher priority. Okay, so there's a few there. Hands up everybody who thinks system node critical is higher priority. Okay, that's actually the correct one. They care more about your node being able to run because if the node can't run, it will never be able to rejoin the cluster if it comes to that. So we're going to make this system cluster critical. We're going to have it request one CPU. Now, we don't have enough to do both of these things at once. But I have, since this is high priority, naively I might think, well, it'll just override the other one, and then things will happen. But, as you might guess, that's not what's going to happen. Why is that pod pending? Well, the answer is right here. It's this pod affinity. And in fact, if we describe the pods, you will see down there, first it said the one node that's available has insufficient CPU. Then it tried to preempt. And it said one node didn't match pod affinity rules because, again, if it evicts that other pod, now the affinity rule that matches that pod won't match that node anymore. Can't schedule on that node. So, how could we fix that? There's a couple of ways. We could remove the affinity rule. We could change the priority of the base workload to be higher than the priority of this so that we're not depending on a lower priority workload anymore. Or we could do what I actually do for this demo and just set its CPU request very small, which since it's doing nothing is fine. So we apply our fixed deployment. We look at our pods again, and now our pod is running because it finally fits into the available CPU on that node. Now, just a couple more things, and then I'll take questions because we're getting down to about the right time for that. Just to wrap up, final thoughts. Like I said, don't panic. I think I said that before. If I didn't, don't panic. You'll figure it out. If it looks weird, it probably is weird. It's not just that you can't understand it. It's legitimately a lot of this stuff is very odd and does not work the way that a normal human brain, and I say that as a neurodivergent person myself, would expect it to work. So just begin with the assumption that, yes, something's gone wrong, but I'm going to figure it out. It's going to be okay. You may not be able to fix it because the fix may be, we need more capacity in the cluster, and your boss says, well, guess what? We ain't got the money this month. But that's fine. You identified the problem at least. Now, I don't spend any time on this, but when you go to the slides online, there's some links to other resources. Scheduling, preemption, and eviction was heavily used for this. Cluster autoscaling goes over both the cluster autoscaler and Carpenter, as well as some of the other autoscalers that I mentioned. There's docs linked there for cluster autoscaler and Carpenter. With that, thank you very much. The first QR code there goes to my slides at the same place as that tiny URL down there. There is the feedback QR code. Please be nice. They were nice last time. I got really good comments. Actually. So I was happy about that. Hopefully this time will be just as good. And it looks like we have about 6.5 minutes if anybody has any questions. Okay, over here on my left. Does he need to turn it on or does somebody else turn it on?
There it goes.
Okay.
So I'm curious how there's kind of this Vim versus Emacs debate on the internet about whether you should use CPU and memory limits, or limits on memory probably yes, but mainly on CPU. Where do you fall on that particular debate?
There are times, and this is because of the things around things that require you to be guaranteed. You will need to set a CPU limit. Usually when you need to do that, you will need to do it so that you can make that pod guaranteed, so that it can access things only guaranteed pods can access, like those reserved CPUs from the reserve pool. There are other things that come into play there too. For example, if you make a pod guaranteed and then you give it a fractional CPU count, you don't get reserved CPUs. But it's kind of a prerequisite. And so in that case, I think, yes, you would go ahead and set some limits. I tend to agree with the blog post the guy wrote, I think it was 2 or 3 years ago at this point, where he said, please, everybody stop setting limits. They don't do anything. In fact, they just cause problems. Most of the time, that's all they do. Over here?
Yeah. So first of all, thank you for sharing your knowledge about this complex topic. And my question was actually very similar to his question, because I read online about this controversy about this requests and limit setting. If you don't really need them, it's better to avoid. At least some people says that. So what I experienced is, and that's been very complicated for me to overcome that issue, was CPU throttling, and I never understood when CPU throttling can be like ignored, because it's a complex topic, and I noticed that no matter what, when you set requests or limit, there will be some kind of CPU throttling, but I never understood when that can be a problem.
The most times that I've seen that be a problem is either when something is starting up that something else is waiting on, so it needs to start up within a certain time, or the other thing is going to give up and time out, or vice versa. It may be that the thing is starting up and is going to need to get to the point in its startup where it connects to something else. And if it takes too long to do that, maybe it fails a liveness probe or something and gets terminated. So, and that is something that you definitely want to watch. There are various dashboards and monitoring tools that will tell you how often you're getting throttled. I would say you probably want to avoid throttling if you can at all. A little bit of throttling now and then is not the end of the world, though.
Thank you.
Over there.
Hi, I would like to ask you about if you have some good resources about how requests and limits affects Java applications, because Java application sets
oh boy,
threads and everything.
Okay, I actually debated putting this in the talk, and I said I'll wait and see if anybody asks. Thank you for asking. So at a previous employer, I actually wrote a whole blog post about this. Java is a special case of all this, because the JVM does its own memory management, kind of hidden away from the operating system, the container runtime, whatever is monitoring things. And so the Java runtime will allocate memory to itself, and then it will parcel it out to the running, I forget what the name is for the actual thing inside the Java JVM. But it will parcel that memory out, and it will garbage collect that memory, but it won't return it back to the operating system. So from the operating system's point of view, everything that is allocated to the JVM is memory in use and can't be reclaimed. And it's a huge pain in the butt. They have started talking about the idea of doing things that would make it easier to reclaim in some circumstances, like the idea of zeroing out garbage collected memory would occasionally make that easier to deal with, or at least you could say, well, okay, we know that we can overcommit that memory page because it's zeroed out. Or we know that if we're taking an image of this container, we don't have to take an image of that page because it's zeroed out. So yeah, the unfortunate reality is that Java is just a pain to work with.
And would you recommend setting request and limit for Java memory then?
Java is also one of those cases where not giving it enough CPU will cause it to fail to start up, because it will just, like Spring Boot is notorious for this. You have to give your Spring Boot applications all the CPU in the world. I think we have time for one more over here.
Sorry. So when I work with the application developers and I tell them, hey, go set request limits, request numbers and limit numbers, and then they come back to me and say, well, I don't know what to set it to. I don't know how much my application is going to need, right?
Yeah.
And so they end up just copying from a previous application usually, right? And then sometimes it works, sometimes it doesn't, and whatnot. So my question is, are there tools or mechanisms that you would recommend to, like, hey, run your application, let it run, set the request limit?
The open source version of that kind of tool would be the vertical pod autoscaler that will look at your actual usage versus your requests. There are a ton of other tools out there that would love for you to pay them money so that they can apply machine learning to your cluster to do that kind of thing for you, some of them even in a predictive fashion.
Okay.
So I think we have one more. Do we have time to squeeze this one last one in? Go ahead. If they cut me off, I'll get you later.
Yeah, a very quick one. Do you have any insights in terms C groups v2? Because it's kind of already there, but not for all of us, depending on what base OSs we're using. So, like, any insights from you how it will improve resource allocation and control of resources?
Wait, improve what now?
Like resource allocation quos, like all the OOM killed kind of situations. And
Yeah, for that kind of thing, I think you really want to dig deep into autoscaling, because a lot of the autoscalers, like for example Carpenter, will actually try to consolidate your nodes so that you're running more nodes. Yeah, I'm getting the red sign. But yeah, Carpenter will try to improve that for you quite a bit. Thank you.